Okay, let's get into it. Today, we're doing a deep dive on the new technical report for the Gemini 2.x model family.
That's right. Specifically looking at Gemini 2.5 Pro and 2.5 Flash.
And our mission today is really to cut past the marketing noise and get straight to the architectural shifts, the performance data, and what's actually changed under the hood with this new generation.
Exactly. And for you listening, whether you're coming from ML, data science, or applied math, this report really does signal a pretty major inflection point. We're talking about a big shift in the capability versus cost Pareto frontier.
hmm
And we're seeing these huge nonlinear jumps in reasoning, true multimodality, and what they're calling next-gen agentic capabilities.
And the headline, I mean, the big takeaway is pretty clear. Gemini 2.5 Pro is being framed as their most capable model yet. It's hitting state-of-the-art on some frontier coding and reasoning benchmarks. But the thing you can see immediately is this massive expansion in multimodal capacity. We're talking about processing up to 3 hours of video in one go.
That's a fundamentally new tool for enterprise applications. It really is. And the way they've defined the product line, it shows a new level of maturity.
So break that down for us. What are the core models in the 2.x family?
Okay, so there are four. 2.5 Pro, that's the apex, the most intelligent thinking model. Then there's 2.5 Flash, which is this interesting hybrid reasoning model. It has a dynamic, sort of controllable thinking budget.
Okay, and the 2.0 models are still around.
Yep, they are. 2.0 Flash is positioned as the fast, cost-efficient, non-thinking model for, high throughput basic stuff. And then 2.0 Flash-Lite is the absolute fastest and most cost-effective one.
So you have this clear tiered structure, but there's a common foundation, right? What are the architectural things that every single 2.x model shares?
Three main things. First, they're all natively multimodal. Text, vision, audio, it's all processed intrinsically, not with some encoder bolted on the side. Second, they all support these huge, long context inputs. Advertises over 1 million tokens. And third, and this is critical for agents, they all have native tool use support baked right in.
Let's talk about the data. When you look at figure 1 in the report, that performance cost curve, just how big is this Pareto shift they're claiming?
It's very significant. Quantitatively, Gemini 2.5 Pro's El Marina score is more than 120 points higher than 1.5 Pro, its predecessor.
Wow.
Yeah, so that's a massive capability jump for the same cost. But what's really interesting is the trade-off you can see in the latency metrics in figure 2.
Okay, what's that showing?
It shows the 2.5 Flash actually outputs tokens slower than the leaner 2.0 Flash. And that difference, well, that's the cost of quality. That hybrid reasoning in 2.5 Flash just needs more compute per token than the straightforward generation of 2.0 Flash.
So even in the new generation, you still have to pay computationally for higher quality reasoning.
Exactly. There's no free lunch.
Let's dig into how they engineered this. The foundation is a sparse mixture of experts, or MOE transformer. How did they leverage that MOE advantage to get these new thinking capabilities without latency just going through the roof?
Well, that's the whole magic of MOE, right? It decouples the total model capacity from the compute you need for each token. It lets the model have, trillions of parameters in total, but it only activates a tiny fraction of them, the right experts for any given token.
And that's what makes the thinking budget viable.
Precisely. It allows the model to do what they call tens of thousands of forward passes, which we'll get to, without the cost per token becoming completely unusable in a real-world setting.
That structural efficiency is one thing, but training a system this huge and this sparse must be an absolute nightmare infrastructurally. The report goes into some detail on the TPU v5P architecture. What were the big breakthroughs there for stability?
There were two main ones. The first they call slice granularity elasticity. Basically, hardware fails all the time at this scale.
All the time.
So the system is now smart enough to just keep training with fewer TPU slices if one part goes down. And the recovery is incredibly fast. We're talking a loss of only tens of seconds of training time per failure. They maintain something like 97% throughput.
Which makes these massive training runs economically feasible in the first place.
It's the only way. The second advance tackles data integrity.
Right, silent data corruption, SDC.
Exactly. A huge problem. It can silently corrupt weights and ruin a model over a long run. So now they use something called split-phase SDC detection. It uses lightweight deterministic replay and per-device checksums.
So they can find the bad accelerator almost instantly.
Within minutes, yeah. They can pinpoint it and just exclude it from the run. It means they're not wasting this gargantuan compute budget on corrupted training steps.
Okay, so that's infrastructure. What about post-training? The report mentions a lot more compute being put into reinforcement learning using these verifiable model-based rewards. Was that the secret sauce?
It was absolutely a huge part of it. That RL investment is what led directly to the big capability jumps. You saw those huge El Marina ELO score gains, 122 points for 2.5 Pro, 111 for 2.5 Flash over the 1.5 versions. That whole RL environment is what made the thinking model concept possible.
All right, let's unpack that term. What exactly does the paper mean by thinking?
So it's an explicit mechanism trained with RL that lets the model spend, and this is the quote, tens of thousands of forward passes on an internal computation phase before it actually generates an answer.
So it's not just a single pass anymore, it's,
Yep.
it's ruminating.
It's allocating compute to reason, to check itself, to refine its plan. Yeah.
And what's interesting looking at figure 4 is that this is controllable. As a developer, what does it mean that I can set a thinking budget in tokens?
It's a total shift in the cost model. You're moving from a fixed cost per token to a variable pay-for-reasoning model. You can crank the budget way up for some mission-critical code generation, or you can keep it low for, say, a simple summary. You get fine-grained control over that quality latency curve.
So let's connect that mechanism to the results. The coding performance jumps in Table 3 are pretty eye-watering. Live code bench performance for 2.5 Pro went from 30.5% to 74.2%.
I mean, that's a 43 percentage point jump in a single generation. It's staggering. And you have to ask, is this real or is it just gaming the benchmark?
Right.
But the paper shows it across the board. Aider polyglots skyrockets from 16.9% to 82.2%. And even on something really tough like Swebench verified with multiple attempts, it climbs from 34.2 to 67.2%.
And that pattern holds for high-level reasoning in math too, right?
It does. AME 2025, which is a competition math test, jumped from 17.5% accuracy to 88%. GPQA Diamond, which is complex scientific reasoning, went from 58.1 up to 86.4%. It really seems like that thinking mechanism is delivering genuine analytical lift.
And that extends to long context, I assume.
Yep. There's still state-of-the-art on retrieval tasks like LFFT, but the crucial thing is they're the only models in the report that can reliably handle a context of 1 million tokens or more. They're hitting almost 70% on the LFT1M benchmark.
Okay, shifting gears to multimodality. Going from 1 hour video to 3 hours, that's a huge deal for practical applications. Analyzing factory footage, medical scans. How did they do that and still stay inside the 1 million token limit?
It was actually a pretty clever, elegant solution. It was all about token efficiency. They managed to reduce the number of visual tokens needed to represent a single frame from 258 down to just 66.
Without losing quality.
Without a major loss in comprehension quality. And because you need 4 times fewer tokens per frame, you can stuff 3 times the video duration into the same context window.
And what about audio? It's more than just transcription now.
Oh yeah. Gemini 2.5 was trained on sophisticated audio generation tasks. We're talking high-quality text-to-speech, native audio-visual to audio dialogue.
And how many languages?
Over 80. And you can control the style, the pace, the emotion. The tech behind it uses causal audio representations, which is what gives you that low latency streaming that you need for any kind of real-time application.
Now, when you put the reasoning and the multimodality together, you get to their factuality mechanism. How is it using its tool calling to get that high SoTA score?
It's basically an internal self-correction loop. It integrates its reasoning with tools, specifically Google Search, to handle really complex questions. The model has an internal thought process. It issues follow-up queries to search, refines its information, and then synthesizes a new verified answer.
And that gets it to what? 87.8% on the FIGTS grounding benchmark?
Exactly. It's a great example of strategic self-correction in action.
Which brings us neatly to agentic workflows. Let's talk about the Gemini Plays Pokemon case study. What did that teach us about 2.5 Pro's ability to handle long autonomous tasks?
Well, first, it worked. The agent beat the game autonomously in about 406 hours on its second try. That's a huge proof point for long horizon task management. And its success really depended on using prompted tools like a pathfinder and a strategist to solve really complex puzzles.
Like 150 action paths, things like that.
Exactly. And it was routinely reasoning over contexts bigger than 100,000 tokens.
But the study also showed some really important limitations. What were the big shortcomings they saw?
2 critical ones. First, screen reading just failed. The agent couldn't interpret the screen visually. It needed the text translated directly from the game's RAM.
So raw visual processing still isn't quite there for these complex environments.
Not yet. And second, and this is super relevant to the long context discussion, they noticed that when the context got really big, like way past 100K tokens, the agent started to just repeat actions from its history instead of coming up with new plans.
Interesting. So there's a difference between long context retrieval and long context reasoning.
A huge difference. The models are amazing at finding a needle in a haystack. That's retrieval. But they still struggle with creating a whole new plan based on the entire haystack. That's generative reasoning.
Let's move to safety and responsibility. A big claim in the report is that the 2.5 models are better at being safe without over-refusing or, giving those moralizing lectures that users hated in the 2.0 family.
Right, and the security evils seem to back that up. Figure 7 and Table 9 show it's more resilient to indirect prompt injection, or IPI, attacks. It's more robust against things like actor critic and beam search attacks compared to 1.5, even though it's a much more capable model.
And they attribute that to adversarial training.
Directly to dedicated security adversarial training against those specific IPI vectors.
They also ran it through the Frontier Safety Framework, the FSF. What was the top-line finding there?
The top-line finding is reassuring. Gemini 2.5 Pro did not reach any critical capability levels or CCLs in any of the areas they tested: CBRN, cybersecurity, MLR&D, and so on.
Oh, there's a but here, isn't there?
There is. The report is very clear about some concerning trends that are basically early warning signals. In cybersecurity, 2.5 Pro showed a really significant capability jump. It solved 6 out of 12 hard key skills challenges tasks that are at the level of an experienced professional.
And that was enough to trigger an alert.
It was enough to pass the FSF's early warning alert threshold for Cyber Uplift Level 1. So it didn't cross the critical line, but the curve in that high-risk area is definitely getting steeper faster than expected.
And what about machine learning R&D?
Equally telling, on a benchmark called R-Bench, the model's best runs scored up to 125% of the best solutions written by human experts. The paper's take was that the model was essentially substituting deep, synthesized knowledge from its training data for human creativity and intuition.
It's just a massive knowledge accelerator. So to bring this all home, the speed of development is just immense. A 5-fold increase on Aider Polyglot in just 1 year.
Right, and this blistering pace forces a really fundamental problem that the paper spends a lot of time on: the evaluation bottleneck.
We're running out of good tests.
We're running out of good tests. The creation of novel, challenging benchmarks is just not keeping pace with how fast the models are improving.
And it's an economic problem too, isn't it?
It's hugely economic. They point out that questions for something like humanity's last exam can cost up to $5,000 for a single accepted question. There just aren't enough experts with the time and knowledge to create these things at scale. The whole paradigm for evaluation is starting to break.
So if you weigh all that, the rapid capability jumps, the early safety warnings, the unsustainable cost of expert evaluation, it really does raise a provocative question for you to think about. Considering all these signals, is the next crucial frontier of AI research less about just scaling the models bigger and bigger, and more about automating the creation of economically valuable, non-saturating benchmarks themselves?